Take a pencil and draw a simple line on paper. That dark mark looks ordinary, but inside it is one of the most advanced materials ever discovered. That's where nanochemistry begins. Let's go a little deeper. Nanochemistry deals with materials at the nanoscale, a scale so small that thousands of atoms fit across the width of a human hair. At this size, materials don't behave the way we expect. Same atoms, same elements, completely new properties. But wait, here's the twist. When materials become extremely small, surface effects dominate. Electrons behave differently. Strength, conductivity, color, and reactivity all change. That's why size alone can transform a material. Here's something even more interesting. Take graphene, a single layer of carbon atoms arranged in a hexagonal pattern. It's thinner than paper, stronger than steel, and conducts electricity better than copper. Same carbon found in graphite. Different structure. Revolutionary behavior. Now let's go even deeper. Nanomaterials are used in medicine, electronics, energy storage, and coatings. They deliver drugs precisely, make screens brighter, batteries lighter, and materials stronger. And then there are alloys, mixtures of metals designed to combine strengths and reduce weaknesses. Steel is stronger than iron. Stainless steel resists corrosion. Tiny atomic changes create massive improvements. Let's connect this to real life. Your smartphone, solar panels, lightweight cars, medical implants, all of them rely on nanochemistry and advanced materials. Before we wrap up, zoom out for a moment. Nanochemistry shows that chemistry isn't finished. It's still evolving, pushing materials to their limits and reshaping technology, from atoms to bonds to reactions to industries, and now to the nanoscale. This is where chemistry stops explaining the past and starts building the future.